So as a quick side note, the above formulas are finding average velocity or average acceleration. The velocity or acceleration over a period of time. So yeah, average velocity, average acceleration means what's the average velocity between 2 points, or what's the average acceleration between 2 points. So for example, the 60 to 100 case, right? A person, or like, I think a better example might be something like a runner, right? A runner doing a race and it's got a 100-meter sprint, for example. Initially, maybe they run at 4 or 5. They're speeding up 1, 2, 3, 4 meters per second, and then they run. Maybe they slow down towards the middle. Maybe they go to maybe back to 3 or 2 meters per second, and then they run back up, and they towards the end they speed up suddenly, go to 7 or 8 meters per second, and then they finish off, and then they stop, so it's like 0 meters per second. So between these 2 points, right, the person's run 100 meters in, let's say, 20 seconds, not terribly fast, but 100 meters in 20 seconds. So the person's traveling 5 meters per second, right? That's the average velocity. Whereas in reality, the velocity graph might look something really messy, or like a bit of a peak and trough and that sort of thing. So maybe the velocity looks something like this, right? But that's the instantaneous velocity over time. Whereas the average velocity would just be saying, okay, 100 meters, 20 seconds, 5 meters per second. That's the average velocity. Whereas, at some point, maybe he was traveling at 2 meters per second. Whereas at some other point, maybe he was traveling at 7 meters per second, and so on. So, yeah. Here's a... similarly for acceleration, it's the average acceleration that's given by this formula, not the instantaneous ones. If you wanted to find the instantaneous ones, that's where calculus comes in, and you want to find the instantaneous rate of change. But in this case, you can just deal with the average and the average velocity, average acceleration. Here's an example. Trisha is walking along a line north to south. She walks 12 meters north, then 15 meters south, and then finally walks 4 meters north again. All of this takes her 20 seconds. First, we're asked to find the distance traveled. Now, the key thing here is that it says distance and not displacement. And so to find the distance, all we have to do is add up all the little distances she walked. So it's a bit like the lap around the field example. We're not actually interested in how far they are from the origin. We're actually interested in where all they went and how they got there. Right? So the distance that they've traveled, I'm going to use D for that. The distance that they've traveled is 12 meters plus another 15 meters plus another 4 meters. Okay? So that's going to be 12 plus 4 plus 15, so that's 31 meters. That's distance. Then part B says to find her displacement from the starting point. That's where we now need to draw in our vectors. So this is how you would usually do these sort of questions. So first she walks 12 meters north. So let's draw in our 12 meters north displacement vector. Or let's put in our origin. Our origin, let's just say, is this point here. I'm going to call it O for origin. And she walks 12 meters north. And then it says that she walks 15 meters south. So what does that mean? She gets to this point and she decides to go the opposite direction. So she goes like this. And this altogether is 15 meters. So if she's gone up or north 12 meters and then back south 15 meters, she's traveled a net distance of 3 meters here, right? And then finally she walks 4 meters north again. So she then decides to go back up this way. So there's somewhere here. So that's 4 meters here. So she was 3 meters south, and then she walks 4 meters north. So that means from 3 meters south to this origin is 3 meters, plus she's got another 1 meter. So that's 1 meter. And so that takes her 20 seconds. So her displacement from the start point would be 1 meter north. Right? If we're asked for the average speed, remember speed is dependent on distance, right? Speed is a scalar quantity, so it's dependent on distance. So speed is distance over time. So in this case, it's a distance of 31 meters over the time of 20 seconds. That's what's given in the question. 31 divided by 20. That's 1.55 meters per second. Right? Unit for distance is meters. Unit for time is seconds. Sorry, unit for distance is meters. Unit for time is seconds. So it's 1.55 meters per second. Now, in the case of the average velocity, in this case we want to have to use velocity as being the displacement, or maybe I would do difference in position, for example. The difference or the change in position, or difference in position over difference in time. So the difference in position at the end of a walk or a journey is just 1 meter. She's only traveled 1 meter north. I'm going to use +1 to denote north and negative to be south. But that's just the sign convention. I could go the other way as long as I'm consistent. But in this case, I'm going to say upwards as being positive, downwards as being negative. And the average velocity is the difference in position and the time taken, or divided by the time taken to complete that difference in position. So it's going to be 1 meter divided by 20. So it's going to be 1/20th of a meters per second, or I believe that's 0.05. Yep, 0.05 meters per second. And we would need to give a direction as well. It's a bit tricky to give a specific, well, I mean, in the end it's north, but so the velocity is 0.05 meters per second. But now do you see how average and instantaneous velocity is quite different? Because when you've got average velocity, right, maybe she was sprinting the first 12 meters. Maybe she was traveling really fast. But see how this final thing here doesn't really account for that? Because maybe she walked the rest of it really, really slow, or maybe she stopped at some point. That's the difference. And not only that, in the 15 meters backwards, she was traveling south, whereas our net velocity is north, right? Or our velocity vector, our average velocity vector is north. So there is a difference between instantaneous and average velocity. But still, velocity is a vector, speed is a scalar, so make sure you give directions for velocity, and displacement and speed and distance, you don't have to give directions, just the magnitude. Okay, so you'll notice that I've been using meters and seconds as my units for distance and time. This is purposeful because they're SI units. SI is Standard International. I think there's an actual real, in a different language, there's an actual expansion for it, but SI Standard International is what I usually call it. But an international, so SI units are an international system of units which ensures consistency amongst academics and professionals. In physics, we always use SI units in our formulas and always give answers in SI units unless asked otherwise. Again, it's always possible to do physics without using SI units, but you just have to be careful as to be consistent. And some formulas, like empirical formulas, for example, they only work with certain unit systems, so you need to be careful with that. Okay, so here's the SI unit, here's the quantity, and here's the respective SI unit. So time is measured in seconds, length is measured in meters, mass is measured in kilograms. Now, don't get confused by that, because we don't measure things in kilometers. Then why do we measure things in kilograms? Well, kilograms just makes a lot more sense for sort of our macro scale things. So it's not grams, it's kilograms as our mass measurement unit. Electric current is measured in amperes. Temperature is measured in kelvins. Amount of substance is measured in moles. And if you do chemistry, you'll see more of that. Candela, I believe it's the other way. Luminous intensity is measured in candela.